So, how do you map a ghost? How do you actually chart something you can't see, like the tremors happening deep inside the Earth? Well, today, we're going to do a deep dive into the incredible science of mapping earthquakes.
And this brings us to a really crucial question. Can we actually trust a map of something that's invisible to us? As we're about to find out, the answer is way more complex and honestly, a lot more interesting than you'd probably think.
Our story today comes from what looks like a pretty dry source, right? A 1980 government report from the Nuclear Regulatory Commission. But believe me, hidden inside these pages is a fantastic scientific detective story about what's real, what we think is real, and the ghosts that our own machines can create.
Okay, so let's set the scene. We're going back to the 1970s in the north-central United States. For seismologists, the scientists who study earthquakes, this whole area was basically a scientific quiet zone. They knew earthquakes were probably happening, but their ability to actually listen in on them was, well, it was pretty limited.
And here's the real heart of the problem. Their network of seismographs, their listening posts for earthquakes, was just incredibly thin. Think about it like trying to hear a single whisper in a giant empty concert hall, but you only have 2 or 3 microphones scattered around. What's the result? All those tiny little tremors, what you could call the Earth's whispers, they just went completely unheard. And that left a massive gap in what scientists understood.
So what do? Well, you build a better net. And we're not talking about a small upgrade here. This was a massive technological jump forward, a really ambitious project to just blanket the entire region with brand new seismic sensors. And the scale of this effort was just immense. Get this, between 1970 and 1980, the number of seismic observatories in that region grew by more than 4 times. That is a huge investment, a major push to finally bring this hidden world into focus.
This new network wasn't just about putting more sensors in the ground. It was also being powered by what was considered super high-tech computing for the time. We are talking about complex algorithms running on programs written in languages like Fortran, which you see here. This was absolutely the cutting edge, a full-on effort to solve this problem with the very best tech they had.
And at first, it really looked like a stunning success. The investment completely paid off. The picture of all the seismic activity in the region got dramatically clearer.
And the numbers really proved it. Take the Wabash Valley, for example. In 1970, the smallest quake they could reliably detect was a magnitude 3.8. Okay, but by 1980, with this new network, they could pick up tiny little tremors as small as magnitude 2.1. Now that is a huge improvement in sensitivity.
What this all means is that, for the very first time, scientists felt like they could finally see this hidden world. It was the perfect scientific success story, right? A problem is identified, a solution is built, and the results give you a much clearer picture of reality. Or so it seemed.
Because as the scientists started looking closer at all their great new data, a ghost started to emerge from the machine. A really strange, totally unexpected pattern that just didn't quite make sense.
Okay, so to understand this ghost, we got to talk about a key concept called the error ellipse. Here's the deal. Locating an earthquake is never perfect. You can't pin it down to a single point. It's more of a best guess. Imagine you're in that huge, dark warehouse again and someone claps. If you only have a few friends listening from different corners, you can't point to the exact spot. Your best guess is going to be an oval-shaped area of uncertainty. That is the error ellipse. And its shape and which way it's pointing depends completely on where your friends, or in this case, your seismographs, are located.
Now this is where it gets really weird. The scientists started analyzing these error ellipses. Logically, they expected the orientations of these ovals to be totally random, pointing every which way. But the data showed something else entirely. They weren't random at all.
What they found was that in certain areas, the ellipses were all lining up, consistently pointing along these specific northeast and northwest directions. It created these apparent trends in the data, lines of seismic activity that looked, for all the world, like they had just discovered a bunch of brand new fault lines.
And then came the big reveal, the stunning conclusion, straight from the pages of the report. The scientists realized that those trends they thought they found, well, they may in fact be an artifact caused by the non-random distribution of seismograph stations. The patterns weren't real. They were ghosts, created by the very tool they had built to see reality more clearly. And this brings us to the really profound lesson from this whole story. It's about so much more than just earthquakes. It's about how we see the world and how the tools we use can literally shape the reality that we perceive.
Just think about what this means for a second. The
The seismograph network wasn't just a passive window looking out at the world. The physical layout of the sensors, the actual geometry of the net they built, was actively creating patterns in the data. And the scariest part? These fake, artificial patterns looked exactly like real geological features. This wasn't a bug in the system or a mistake. It was a deep, fundamental insight into the very nature of measurement itself.
Let's put it as simply as possible. The tool didn't just find the earthquakes, it was creating patterns of its own. It was drawing its own ghosts right there on the map. And that leaves us with a final and pretty fascinating question to think about. As we use more and more powerful tools to map everything, from the human genome to our own social networks, what patterns that we see in our world are actually real, and what are just a reflection of the tools we're using to find them?